And welcome. We are talking today about section 5.2, integration by substitution. Our first learning objective is to use the method of substitution to find indefinite integrals. We're actually going to use this for a couple of our videos just to spread it out a little bit because these examples can get a little long. Okay, so this is just our first little investigation just to get a sense of what this method is like. So up until this point we know power rule, for instance. We know how to work with an exponential function, at least a simple version. We can deal with some radical stuff. So this doesn't exactly look like our typical form, and I want to point out that this is pretty close. It looks like something squared, so that's relatively close to our standard form for power rule, but it turns out it's not really close enough, actually. So we're going to try this a couple of different ways. First, we'll just do some algebra and then use the rules of integration that we've already established. And then we'll follow that up with something a little more creative. We'll try to write the integrand with this notion of a substitution, rewriting a portion of it and calling that some new letter. First, the algebra strategy. So really all we're asking you to recognize here is that since you've got something squared, we could do our little foily deal, make this 3x plus 1 times itself, distribute, and then we'd have, after combining like terms, we'd have this expression. And that's actually great. Everything in here looks like our variable x raised to some kind of power. Remember, we can get a little bit sneaky with this guy over here. This is technically x to the 0. And we can go through our power rule in a standard way. So we should take a look at this and just kind of identify the pieces. We've moved past 5.1, but I recognize if this was your initial exposure to integration, then these strategies probably aren't mastered yet. So if we take our 9x squared, for instance, our power rule is going to say, leave the 9 alone. And then we've got x, the power goes up by 1, so we're up to cubed. And then we're supposed to divide that expression by this new power. And right, so 9 divided by, that looks like a q. Great, my 6-year-olds would be happy about this. 9 divided by 3 is going to give us 3. We'd have x cubed left over, and there's our first term. So lather, rinse, repeat, and that gives us these other guys. So 6x goes up to x squared. Divide by that new power gets us a 3, 6 divided by 2. And then this fella is going to go from x to the 0 up to a power of 1. Divide by 1, that's not really going to change it very much, so we'll just have x. And then this thing we'll probably forget pretty frequently, but is an important element here, this plus c, to represent the fact that this integral really is a whole family of antiderivatives. Okay, so that was part A. This was the strategy that we should have fairly strong confidence in giving us a successful answer. And now we're going to get a little more creative and try to kind of compare this creative strategy with something that we know should work out. So if we define u, so we're calling this new letter, we're just making it up, but the strategy is often called u substitution, although there's nothing special about this letter. We're basically replacing this thing in parentheses with some new letter. This is purely psychological, but if we do that, then you have to admit this expression does change a little bit. Oh no, yellow's always bad. So if we take our expression here, we're literally just calling that u. Now, there are some challenges, and we have to acknowledge those challenges. We're going to acknowledge the fact that now this variable, u, doesn't match with this differential term. And I want to remain, I hope I've been careful up to this point, remain careful in distinguishing that this differential really is the only thing that is directing us toward what is the sort of a quote official variable here. So the fact that this is a u inside of here and it's a dx for the differential should make us pretty concerned about the validity of this. However, we're going to push through, and we're going to, I'm acknowledging that this probably wouldn't be your natural assumption, but I'm going to put a little question mark as part of this expression so that our adventure here will actually turn out being okay. So I'll just point out we're appending this little question mark here as a factor of our integral, of our family of antiderivatives. So just to revisit the actual integration here real quick, we've got u squared. We're pretending that this is going to work out okay, and we're going to get, by power rule, that the exponent goes up by 1. We'll divide by that new exponent, And as always, we'll get this constant of integration that tacks along for the ride. Now, I'm using a little subscript here because it's going to go through some changes, some growing pains here, but this will get modified a little bit as we move forward. Okay, so hopefully what I'm trying to convince you of, or what I have convinced you of, is that we can kind of do this as long as we're careful about acknowledging that we're missing a little bit of information when we integrate u, when the differential term is actually telling us that x is the real variable. So this is just us going back and replacing. So here's the 1/3, there's the question mark, none of that's changed. We're just replacing, or we could sometimes call this back substituting. We're getting rid of the u's and going back to the x's again. Well, why do we go to the u's if we're just going to get rid of them? It was a psychological device. It helped us see this as something squared in order to make this work. But really, we are going back and saying, look, this thing, this u, was really a figment of our imagination, and it was in fact 3x plus 1. Okay, and then I want to do a little bit of expansion and comparison here, because remember, we have a part A to this problem, which we should feel pretty confident about. We ought to feel good about our answer in part A because it just used power rule and algebra. Of course, how often do we feel good about algebra? All right. Well, so let's see. Do I have another color? We could try green here. Sorry if you are red-green colorblind. I'll try to separate these. So this expression, this guy right here, is we can expand using, well, not exactly FOIL, or repeated uses of FOIL if you'd like, or Pascal's triangle, or binomial theorem if you're familiar with these guys, or Wolfram alpha, you know, whatever. I'm not judging. So this expression expands there, and we get this big x cubed deal. And then maybe this is the time where we could distribute that 1/3. So we'd have 1/3 times 27x cubed, 1/3 times 27x squared, and so on. That worked out great for these first three terms because these are all divisible by 3. Plus 1 divided times 1/3. All right, fine, it's 1/3. And then really all we're doing right now is playing around with this because this is our answer to part B. Doesn't really look like our answer to part A yet, although it's getting kind of close now. So the last thing let's do is say, by the way, here's a plus 1/3. We can just kind of include this extra constant with this other guy. Because if we take something times 1/3, we're basically saying, look, we'll just tack on this extra guy here. We're not totally sure what it looks like yet, but we'll sort of pull that off to the side. Okay. So just as a reminder what we're up to, this part B thing, which is what we're up to at the moment, we're speculating that this will actually pan out right. And it actually does agree with the integral in part A as long as we're kind of careful about this comparison. So here was our answer from A, if you recall. And then this whole deal over here is our answer from part B. And if we compare these guys, there actually is some real similarity. In fact, all the variable pieces, we have an x cubed term, an x squared, and an x term. They all line up. The coefficients aren't quite right, but they would be perfect as long as this was exactly 1/3. And that's the observation to come to here. So if this was 1/3, then we would have this coefficient would be 3, because it'd be 1/3 times 9. The second coefficient would also be 3. This 3x would go away, because it'd be 1/3 times 3. We'd have just 1x. And this seems kind of unmotivated until we realize that there actually is something consistent going on here. And this example is called an initial investigation. This is not generally how we'll process this, because we're just trying to get our feet wet. But it's not an accident that this 1/3 came out of it. There is a lesson we can learn. So if we go back to our choice of variables, we picked u equal to 3x plus 1. And one thing you might notice is that if we took derivatives here, we actually said, how does u change with respect to x? We'd get just this constant 3. Okay, well, that doesn't seem quite right. That's a 3, not a 1/3. But if we reorganize stuff, then we'd say, look, this du, and a little piece of me dies every time this happens, but all right, whatever, I'm going to draw it. It's essentially like we're multiplying by dx and then dividing by 3. So we have a 1/3 that joins du on the left side, and then we've got a dx by itself on the right side. So basically what this substitution process is training us to do is you have to replace you have to replace x's with u's, but you also have to pay attention to how this differential thing is going to get modified, because dx has got to get out of that integral as well. So moving forward, we're going to have a more polished strategy for this, but basically this 1/3 came out of the derivative of this u expression, the substitution that we picked, once we moved that 3 over. So basically this process, the picking the u, taking the derivative, is the basis for this technique we're calling integration by substitution. And just to, I'll show this again at the start of the next video because this stuff is always a little bit hard. But this is our basic strategy. We're going to pick some value of u just like we did. Simplifies is certainly put in quotation marks here because it's not always clear what simple means. We're going to rewrite everything in terms of some u's, and all the dx's and x's go away. We compute the integral because the whole point was that it should be simpler. And then before we're done, we go back and throw our x's back into the mix. So by and large, this is essentially the process that we just went through. So when we come back in the next video, we'll try out a couple of more